Hello and welcome to Principles of Mathematics lesson number 12. In this lesson, we're going to be looking at the important concepts of prime and composite numbers. We will be basically looking at the definitions of prime and composite numbers, the number of divisors of any whole number, and the fundamental theorem of arithmetic. Here we have a visual representation of the number 18 in three different ways. So here we can see 1 times 18, 2 times 9, and 3 times 6 as possible factorizations for the number 18. And the positive divisors of 18 would be 1, 2, 3, 6, 9, and of course 18 itself. The 1 and the 18 are the trivial factors, right, for any number. Itself and 1 are always going to be factors. These other ones are the non-trivial factors. Here we have a table that actually takes quite a bit of time to develop, because for each number that you see on the top, these are the numbers between 1 and 38, so less than 38. When I say between 1 and 38, that does not include 38. Basically, I should say between 0 and 38, so including 1 and 37, but not 0 and 38. So these are the number of positive divisors for the numbers listed below. So there's only one number between 0 and 38, or we should say less than or equal to 37, that has only one divisor, and that's only 1. Here are all the numbers between 0 and 38, or less than or equal to 37, that have 2 divisors. These are very special numbers, right? Because as we're going to see, their only divisors are 1 and themselves, okay? They have a special name. We call them prime. We'll get to that in a minute. These numbers here have 3 divisors. The numbers you see listed in this column each have 4 divisors. This number has 5 divisors. Let's just take a look at 16 and see why that makes sense, right? 16, we know that has the following divisors, right? 1, 2, 4, 8, and itself, right? That's why 16 is in this column, right? Take a look at these numbers and convince yourself that each of these numbers has 6 divisors. That means 6 numbers that go into it perfectly. You're not going to find any number with exactly 7 divisors, but you will find that these 2 numbers, 24 and 30, have 8 divisors, and the number 36 has 9 divisors. Check it out for yourself and convince yourself that it is so. As I mentioned in the last slide, there's something very special about these particular numbers in this second column that have exactly 2 divisors, and those divisors are 1 and the number itself. These special numbers are called prime numbers. In other words, a prime number is a natural number greater than 1 whose only factors or divisors are 1 in itself. All right. Note that all these other numbers, including the ones with only 3 divisors, have at least one factor or divisor other than 1 in themselves. These numbers that have at least one factor other than 1 in themselves are called composite numbers. So natural numbers greater than 1 are categorized into two groups. One is the group with only exactly two divisors, and then there's everybody else, right, which has more than two divisors. Remember that both of these concepts are significant, but of particular interest to us are going to be prime numbers, as you will see. So there's one number that we seem to have been ignoring, right? And that is 1, right? So where does that, fall into? Which category does that fall into? Prime or composite? Well, the fact of the matter is that 1 is neither, okay? We consider 1 to be neither prime nor composite. So to reiterate, remember that a prime number is any positive integer with exactly two distinct positive divisors, namely 1 and itself. Note that when we say a positive integer, that's another way of saying a natural number, okay? So those two phrases are interchangeable. Composite numbers is basically any natural number or positive integer greater than 1. Notice it's kind of moot to say positive, because when we say greater than 1, it's obviously going to be what? Positive. So that's why in the second part they dropped it. All right, greater than 1 that has a positive factor other than 1 and itself. Okay, so we've seen that the majority of numbers generally fall into the composite category, and we know that they're all going to have more than two distinct factors. All right, so let's see if we can show that each of these numbers are composite. Remember, all I have to do to show that numbers are composite is find a single factor other than 1 or the number itself. Now, this number right here, obviously, we can easily find at least one factor other than 1 and itself, and that would be what? 2, right? Because it's an even number, so 2 divides it. 2 divides 1564, therefore 1564 is composite. Why is that? Because you remember 1 and 1564 are always factors of 1564, so we just found one other, and as long as there's one more, you can stop. You don't need to show any more. You've already shown that it's composite. See if you can show why this one is composite before you come and watch the rest of the video. So pause it, see if you can show that this is a composite number. Okay, so now this is an odd number, so I can't do it as quickly as I did this one. For this one, I'll try to see if perhaps 3 goes into it, because I know 2 doesn't go into it. Maybe 3 goes into it. So remember, I have to add the digits and see what I get. Now 2 plus 7 is 9, and 1 is 10, and 8 is 18, right? Now we know that 3 divides this sum. Therefore, 3 divides the number itself, and therefore 2781 is composite, like so. Okay, so how would we show that these numbers are composite? Well, remember that we know that, for example, for 1001, 2 doesn't go into it. Now, it's easy to see that the sum of the digits is 2, so 3 doesn't go into it. That means 9 doesn't go into it. We know 5 doesn't go into it. Since 2 and 3 don't both go into it, we know that 6 doesn't go into it. We can try 7 and 1001 divided by 7 is 143. So there we have found ourselves a factor of 1001, which makes the number not prime. Therefore, it's composite. So we just showed that 7 goes into 1001. Therefore, 1001 is composite. Why? Because 7 is a number other than 1 and itself that goes into it. So therefore, it's composite. In fact, there's another prime number that goes into that. Can you see what it is? Remember the divisibility rule for 11? If you take the sum of the powers, the place values that correspond to powers of even powers of 10, so that would be, remember, this is the 10 to the 0 location, and this is the 10 to the 2 location, and this is the 10 to the 1 location, and this is the 10 cube location. So if we take the sum of the even ones, meaning the 1 and 0, and take away from that the sum of the odd ones, that would be 0 plus 1. What do we end up with? We end up with 1 minus 1, which is 0, right? So what does that tell you? That tells you because 11 goes into 0, don't get confused by that. I'm not saying 0 goes into 11. That's a no-no, right? But 11 does go into 0. In fact, all non-zero numbers go into 0, right? How many times? 0 times. So therefore, 11 goes into 1001 as well. So we just showed that there's another factor. In fact, 11, we didn't have to. It was just a good practice for the divisibility rule for 11. All right. Now, we've seen this next creature before. Do you remember it? And when we were discussing it, I told you there's something interesting about this number. Well, this expression, which does eventually become a single number. And that is the fact that here on this first term, we're multiplying a bunch of odd numbers. Remember, it doesn't matter how many odd numbers you multiply. The result is going to be odd. And then at the very end, you throw in a 1, you add 1. So now what happens when you take an odd number and you add 1 to it? Well, it's going to make it even, right? And clearly it's larger than 2, so it's even and larger than 2, therefore it is composite, because all even numbers larger than 2 are divisible at least by 2, right? So therefore there's at least that one other factor that they're divisible by, so they're composite. 2 is very special, remember that. Why? Well, it's the very first prime number, right? That's one fact. Another fact, well, that makes it also the smallest prime number. Finally, think about what else is special about 2, right? It's the only even prime number. There's no other even prime number. All other prime numbers are odd, because if a prime number is even and it's larger than 2, then it's going to be divisible by 2, just like what we discussed over here. So it's going to be divisible by 2, so it's not going to be prime. It's going to be composite. Okay? So that's what makes 2 special. All right, next we want to look at the really important topic of prime factorization. Notice that composite numbers can be expressed as products of 2 or more whole numbers greater than 1, right? Each expression of a number as a product of factors is a factorization. Let's look at some examples. Take the number 12, for example, right? I can write 1 times 12, right? I can write 2 times 6. I can write 3 times 4. Or maybe I can write 2 times 2 times 3. Or 1 times 2 times 6, right? All of these are possible, or any other possible factorization that you can think of, right? Now, all of these, anytime you take a number, a natural number, and write it as a product of 2 or more factors, what you have is a factorization. And each of the numbers in each of these factorizations is considered a factor of that number. So here, the original number we were dealing with, it's 12. However, notice that of all of these factorizations, one stands out, and that is this one. Why is that? Because every number in that factorization is a prime number. So that's precisely why it is called the prime factorization of 12. Now, we're going to find a very nice system for finding prime factorizations of a number, and we'll actually discuss 2 methods, and I'll tell you which one I prefer. So we'll get to that soon. Now, one of the most important results in arithmetic is called the fundamental theorem of arithmetic, also known as the unique factorization theorem, which tells you every composite number can be written as a product of primes in one and only one way, except for the order of the prime factors in the product. So, for example, if you take 60 and find all the factors, right? Now, the first time I'm going to do that for the way that you're familiar with a tree, right? So we know 60, for example, goes into 2 and can be broken up into 2 times 30, and then 30 can be broken up into 2 times 15, and then 15 can be broken up into 3 times 5. So you can see we can write 60 as 2 times 2 times 3 times 5, right? So, correction, I mean 2, yeah, we were right. 2 times 2 times 3 times 5. So I had it right the first time. All right, so basically 2 squared times 3 times 5, correct? So now, what we're saying here is that this factorization, which is, by the way, a prime factorization, because if you notice, except that this is written as a power, if I were to write it out separately, it would be 2 times 2 times 3 times 5, right? So, in fact, every number in this factorization is prime. So, the only way you can make this any different is by changing the order. But that makes no difference. So, that's why we say the prime factorization of a number is unique, except perhaps for the order in which the factors are written, which doesn't matter anyway because of the commutative and associative properties. So this prime factorization for every composite number is unique. So one method of finding prime factorization is basically to do what we did, we'd start with whichever factors come to our mind, and we go ahead and keep going until at the end of each node we have a prime number. Then we can take all the primes that we see at the end of the nodes and multiply them, and that's the prime factorization of the number. Now, this works, but it's a little bit messy. So now that we have divisibility rules at our disposal, we can do this in a much neater way. Let me show you. So the neater way works like this. You go ahead and write the number that you want to find the prime factorization of and draw a line next to it, okay? Now, we can create some spaces like this. Now, here's what you do. You ask yourself the same question repeatedly. At each step, you're going to ask a simple question. What is the smallest prime number that goes into this number on the right? Now, 84 is, of course, even, so we know the answer is going to be what? 2. 2 is the smallest prime number that goes into any even number, right? So we go ahead and divide 84 by 2. We get what? 42. We write the result on the right side. Remember, we're going to reserve the left side for only prime divisors, right? So now we repeat the process with 42. So ask the same question. What's the smallest prime number that goes into 42? Well, I think you know, since it's even, again, it's going to be 2. So go ahead and divide. 42 divided by 2 gives you 21, right? And ask the same question again. What's the smallest prime number that goes into 21? I think you know that this time it's not going to be 2, but rather 3. So you got to know your first few prime numbers. That's really helpful. So 2, 3, 5, 7, 11, 13, 17, 19, 23, etc. So now ask yourself, so go ahead and divide 21 by 3. You get what? 7. So write the result here on the right side. Now, for the first time on the right side, we've come up to a prime number. So this is when you're very close to the end of this algorithm, because now what's the only prime number that can go into a prime number? If you think about it for a minute, you'll realize that it's what? Itself, okay? So once you hit a prime number, you just have itself over here, and then you divide and you get 1. So you put the 1 on the other side. Now, once you reach this 1, you're done. So the end of the process of prime factorization has come and you're finished. Now, the really nice thing about this method is that you notice you get all your primes in order from smallest to largest, and you can quickly write this particular form of the prime factorization using powers. So we have 2 squared times 3 times 7. See how nicely that works out? Now, I want you to pause the video and see if you can do that for 495 on your own. Create this kind of a table for 495. So write 495, draw a line, and then get to work. Pause the video and see what you come up with. All right, so with 495, I know that because of that 5, the temptation is to start with a 5. But I recommend to you to always look for the smallest prime number, because it's going to keep this table much nicer and more organized. So just quickly add them, see if it's divisible by, the sum is divisible by 3. So 4 and 9 is 13 and 5 is 18. Yeah, 18 is a number divisible by 3. So this number is divisible by 3. So go ahead and start with 3. So now we divide 495 by 3, right? So I know 450 divided by 3. See, we have to use some of the tricks we've learned, right? So I'm going to write 495 as 450 plus 45. Would you agree? That's true. See how nicely that works out? Go ahead and divide it by 3. So now I know I'm going to get 150 plus 15. So I get 165, right? So I write the 165 over here. Now, I look to 165, and again, always before you try 5, try 3, okay? So 1 and 6 is 7 plus 5 is 12, so I know that's divisible by 3, so this number should still be divisible by 3. So we go ahead and write the 3 to its left and we divide. So now you can use the same trick I just did for 165 divided by 3, so you don't have to use a calculator. I'm going to write 165 as 150 plus 15 divided by 3. So of course that's going to give me 50. 150 over 30 is 50, and 15 over 3 is 5. So I get 50 plus 5, which is 55. So I write that result on the right side. Remember, on the left side, we have nothing but primes. So now I know that I've reached a number that is no longer divisible by 3, because 5 plus 5 is 10, and 10 is not divisible by 3. So I go ahead and try 5 now. So I know that 5 goes into 55 11 times. So I write that here. And notice that 11 is a prime number, so the only prime number that goes into a prime number is itself. You may be thinking, what about 1? But remember, 1 is not prime. So my question at each step is, what is the smallest prime number that goes into the number on the right? And the answer is the only prime number that goes into this prime number is itself, until you get 1, right? So we can stop there, and that's all we need. So remember, once you hit that 1, you are done. Okay, so now you just start from the top on the left side and you write your prime factorization. So you say 495 equals 3 squared times 5 times 11. Very nice, very systematic, very simple, and always gives you fantastic results. So this algorithm is a lot cleaner than this. This was nice, you know, and it's really a good technique for the youngest students, right? But as they start to mature a little bit and can handle a little bit more intensity, you would go ahead and give them this because it's so much more efficient. All right, here are a couple of problems that I would like you to pause the video and try, and then come back to see if our answers agree. All right, now if you have a solid grasp of the divisibility rules for the ones we've discussed, 2, 3, 5, for example, remember, we're really interested in primes here, right? We're doing prime factorization. So the other prime other than these that we've discussed has been 11, right? So then you should be in great shape. So we start with 260. Remember, draw a line. Now, what is the smallest prime number that goes into 260? Well, it's even, right? So 2, divide, you get 130. Again, since this is even, the smallest prime that goes into this is 2. You end up with what? 65. Now 65, remember, is odd. With odd numbers, always try 3 before you jump to 5. Now 6 and 5 is 11. It's not divisible by 3, so we have to go to 5. 65 divided by 5. Let's see if you can do that quickly. That's 50 plus 15 divided by 5. You get it? 50 divided by 5 is going to give you 10, and that's going to give you 3, so 13. Now we've reached a prime number, right? Remember, 13 would be like the next prime in this list. So what is the smallest prime number that goes into a prime number? Well, itself is the only prime number that goes into it. So once you hit the 1, you're done. So you would write the prime factorization of 260 as 2 squared times 5 times 13. All right. Now go ahead and, if you haven't done so already, pause and do the same process for 360. Okay, welcome back. We know that we can start with 2 because 2 goes into 360. How many times? 180 times. It's even. We can go with 2 again. 18. 180 divided by 2 is 90. We write the answer here. What goes into 90? Well, it's still even, so we stay with 2 as long as we can, so no rush. 45. Now I've reached an odd number, so it's not going to be 2 anymore. That's going to be dividing into it. So now I know that 4 plus 5 is 9, and 3 goes into 9, so it goes into 45 as well. So how many times does 3 go into 45? 15 times. Once again, I've reached a number here that is odd. So 1 plus 5 is 6, so I know I can still go with 3. That gives me 5, and now 5 is prime, so I know the only prime that goes into a prime is itself. And then finally I end up with 1 on the right side. So remember, you divide the right side by the left side and then write the result on the bottom right, okay? Right below that number on the right. All right, so, and then you keep going till this number on the right ends up being a 1. That's when you know, okay, I can stop. I've finished the procedure. So now 360 is going to be, how many factors of 2? 3. So 2 cubed times 3 squared times 5. That's how you find prime factorizations of natural numbers. All right. One topic of interest for us is finding the number of divisors of any given number. For example, let's find out how many positive divisors does 24 have. Well, remember that we're not asking how many prime divisors, but how many divisors it has, right? Any divisors, not just prime ones. So notice we know that all of these numbers go into 24, including 24 itself, right? So now if the number gets really large, it becomes quite a task to try to write all the factors like this. Oftentimes we just want to know the quantity, how many are there? And what really helps us with this is prime factorization. I'll show you how. If you find the prime factorization of 24 using the method we discussed, you start with 2, you get 12, you go with 2 again, you get 6, 2 again, you get 3, and 3, you get 1. So basically, as you can see, 24 can be written as 2 cubed times 3. Now, if you think about it, what are the factors of 2 cubed? So all you have to do now is find the number of factors of this one, find the number of factors of that one, and then apply the what? The good old fundamental counting principles, and you'll have the total number of factors for 24. Now, the positive factors of 2 cubed are simple. They're just going to be 2 to the 0, 2 to the 1, 2 squared, and 2 cubed itself, right? And for 3, the factors are going to be 3 to the 0 and 3 to the 1, right? So 2 factors, right? So now the number of divisors for 24 can now be obtained. So notice that for each factor to a given power, there's one more factor than the exponent, right? So when you have 2 cubed, that's actually going to have 4 factors because the 2 to the 0 always has to be counted as well. So for 3 to the 1, we know that there are 2 factors, and that's one more than the exponent, right? So once you've written a number in its prime factored form, then all you got to do to figure out the number of divisors or factors of that number is to take each of the exponents for the unique bases here and add 1 to them and multiply by each other. So here we're going to get the number of divisors of 24 is going to be 3 plus 1 times 1 plus 1. So we end up with 4 times 2, which is 8. And that's how you do that very simply and efficiently. And of course, you know that we always like to generalize in mathematics. So if P and Q are different prime numbers, M and N are whole numbers, then P to the N times Q to the M has exactly N plus 1 times M plus 1 positive divisors. And you can also generalize to more than just two. You know, if you have several powers of prime factors, then the same exact thing can be done with the larger number of factors as well. All right, so we want to find the number of positive divisors of 1 million. Now, 1 million is a very kind of nice special numbers, right? A number. So we could go through our standard process of finding prime factorization. So here we write 1 million, we start with 2, that gives us 500,000, etc., right? And then 2 gives us 250,000, and we can continue. And that's fine, all right? Now, it will be, you know, it will take a little bit of while of time, but if you notice, you can also do this with this special kind of number. Notice that 1 million is none other than 10 to the 6, right? Now, because 10 has two nice factors, right? 2 and 5, we can go ahead. In other words, if you just think of the prime factorization of 10 rather than 1 million, then you just get 2551, right? That's it. So we can write 2 times 5 to the 6, and we end up with 2 to the 6 times 5 to the 6. Now, that's a very fast way of reaching this as opposed to this. Now, this works in a fantastic way for most numbers, but sometimes when a number lends itself to doing so, you want to use any clever opportunities that are available to you to save some time. So now, notice we have a product of two factors, each with 6. So the total number of factors for 1 million is, remember, take each of those and add 1. So 6 plus 1 times 6 plus 1, so we get 7 times 7, which is 49, just like that. Okay? Make sure that makes sense and before we proceed. All right, here's another one of those. See if you can come up with the number of positive divisors for this one before you watch me do it. All right. So notice that here, if we take that 210 that's being raised to the power of 10 and find the prime factorization, we start with 2, we get 105, 3, we have to go to 3 now because 105 is no longer even, so about 1 plus 0 plus 5 is 6, so it's divisible by 3, so we divide, we get 35, and then we have to jump to 5 because 35 is no longer divisible by 3. Remember, at each step you're asking what's the smallest prime number that goes into this number on the right, right? And of course the answer here would be 5, and then we get 7 when we divide 35 by 5. And now we say what's the smallest prime number that goes into this prime, and the answer for a prime number is always itself. Go ahead and divide and you get 1 on the right side. That's when you know you're done. So I can take 210 to the power of 10 and write it as quantity 2 times 3 times 5 times 7 to the power of 10. So now I have 2 to the 10 times 3 to the 10 times 5 to the 10 times 7 to the 10. So by the fundamental counting principle and the understanding that we have about the number of factors of each of these powers, which is going to be one more than its exponent, the total number of factors is going to be 10 plus 1 times 10 plus 1 times 10 plus 1 times 10 plus 1, right? Because they're each 10. So that's basically 11 to the 4. So if we just figure that out, you'll see that's quite a few factors. So 11 to the power of 4. And we get 14,641 factors. So this is really nice because it helps us pretty much find the number of factors of any number very quickly and efficiently without having to sit there and actually find all the factors. Now, as far as finding out whether a number is prime or not, that's a trickier proposition. So what we have to do is we have to basically check divisibility for all the primes that are less than the given number. That makes sense, right? So for example, to determine if 97 is prime, we must try dividing 97 by prime numbers 2, 3, 5, and so on, as long as the prime number is less than 97. So you must be thinking, well, that could be a bunch of primes. Well, that's true, but there is going to be a theorem that's going to help us out a bit here, so not to panic. Now, if none of those primes divide 97, then 97 is considered to be prime. Upon checking, we determine that 2, 3, 5, and 7 do not divide 97. So now we get clever. We say, assume that there's a prime number p greater than 7 such that p divides 97. In other words, that's a factor of 97. That would make 97 over p also a factor of 97, right? Let's see why that's so. Notice that if 97 is divisible by p, that means there's some constant c, so that when I multiply it by p, I get 97, right? And what happens if I divide this 97 on the right side by p? Well, I get p times c. Remember, we're basically dividing both sides of this equation by p, right? So we get p times c over p. Now notice that here the p's cancel out, so we get 97 over p would be that constant. So that's basically going to be that means basically that 97 over p is also a perfect result. Therefore, 97 over p is also a factor of 97. It divides 97. Now notice that this p is going to have to be greater than or equal to 11, because remember, we already have talked about 7. So the next prime after 7, remember, there's a gap between 7 and the next prime, because what's after 7? 8, 9, 10, not prime, not prime, not prime. So the next prime is 11. So p has to be greater than or equal to 11, right? So if you divide a number greater than or equal to 97 by a number greater than or equal to 11, the result of that division is going to be less than 10. And therefore, it can't possibly divide what? Divide 97. But we had established that 97 over p should divide 97. So that leads us to a contradiction, and therefore telling us that a number greater than 7 is not going to be a prime factor of 97. You really have to think about these things for them to make sense. Don't give up. If you need to watch it more than once for it to make sense, do so until you get it. All right. What that basically accomplished for us is it gave us this nice little trick. If n is composite, then n has a prime factor p such that p squared is less than or equal to n. Okay? So if n is an integer greater than 1 and not divisible by any prime p such that p squared is less than or equal to n, then n is prime. So this is really kind of nice and interesting, because what this tells me is that if I want to check, for example, if a number is prime, a number larger than 1, all I have to do is basically look for a prime less than or equal to its square root. That's what it boils down to. So if I roughly explain this as taking the square root of both sides, you end up with p has to be less than or equal to square root of n. So that really dramatically reduces the number of primes that we have to check. Consider this problem where we're trying to see if 397 is composite or prime. So here's what you're going to do. See, textbooks drive you crazy because suddenly they throw a fact at you like this and you're going, whoa, wow, how? How did you know that they should stop at 19? Well, there's a nice trick I'll show you very quick. So basically, take the square root of the number you're trying to determine the nature of, and there you are. So the square root of 397 is 19 point and some change, right? So that's why you know that you want all the primes p so that the square of them is going to be less than that, right? So you want all the primes whose square is going to be less than that. So as you can see, 19 is going to be the highest value that is going to be part of the primes, because what's the next number? What's the next prime number? The next prime number is 23. That's too much, right? So because 23 squared is going to be larger than 397. So that's why we know 19 is the highest value prime that we need to check. So basically at this point, you know that in order to determine if 397 is prime or not, all you have to do is check divisibility by these primes. And if you check it, just sit there and divide. It's very simple. You just go, well, we know it's not going to be 2 because it's not even. You try 3 because the sum is not divisible by 3. 3 plus 9 is 12, plus 7 is 19, which is not divisible by 3. It's not 5 because it doesn't end in 5. It's not 7 because 397 divided by 7 is not a whole number. And the same thing goes with all the other ones, like 397 divided by 11 doesn't work. 397 divided by 13 doesn't work. 397 divided by 17, see? You just check them quickly. And 397 divided by 19 itself also doesn't work. So basically, we realized that given that we couldn't find the prime such that the square of it is less than or equal to 397 and it goes into 397, we conclude that the number 397 is prime. So this nice little fact that we learned on the previous slide really cuts down the number of prime numbers that we have to check. All right, how about 91? Composite or prime again? all we have to do is we have to check divisibility by the primes less than or equal to the square root of the number. So take the square root of 91. So 9 point something, right? So notice that the only prime that can come up to this point, up to less than or equal to 9, that's going to go up to 7, right? So you want to check primes up to 7, because what comes after 7 is 11, which is too much, right? That's too big. So the only primes of interest are 2, 3, 5, and 7. Now, you ask yourself, is 91 divisible by any of those 4 numbers, right? 2, 3, 5, or 7. And if you do, you realize 91 is divisible by 13. And I believe that's, by 7. And I think it goes into, 7 goes into 91 13 times. So that's how you know 91 is composite, because it obviously has a factor 7, which is other than 1 or itself. One other way, of course, if you can find to find all the primes less than a given number, is to use what's called the sieve of Eratosthenes. Now, if all the whole numbers greater than 1 are considered or placed in the sieve, the numbers that are not prime are methodically crossed out or dropped through the hole of the sieve, and the remaining numbers are prime. So it's a very, very rudimentary and arduous process. Basically, you write down, say, numbers 1 through 100, and you just start going through and you go, okay, I know that's not prime by definition. Then you move to 2, 3, and the ones you know are prime, you leave alone. And then you just cross out all the ones you know are not prime, right? Like these you can easily cross out because they're all multiples of 10, can't be prime. These you can get rid of very quickly because you know they're all evens, right? So all these even numbers greater than 2 can easily be crossed out, right? You can get rid of all these because these are all the multiples of 5, right? And of course, they're multiples of 5, so 5 goes into each one of them, so they're not prime. So it's, you can be clever about it and do this very quickly, but the other method that we have is much more efficient and sophisticated. All right, so that brings us to the end of the lesson. So we will follow our usual tradition of looking at some homework problems now. All right, so here's an interesting problem that helps us understand factors better. We have the fact that 32n is equal to 2 to the 6 times 3 to the 5 times 5 cubed times 7 squared times 11 to the 4. We want to know why this particular expression, which of course can be multiplied to give a number, is a factor of this number n. Now remember, they're giving us 32n, so let's go ahead and start by writing that. Of course, as always, see if you can try to explain this on your own before you watch, if you have some clue as to how this should be done. That's always better. So we have 32n equals 2 to the 6 times 3 to the 5 times 5 cubed times 7 squared times 11 to the 4, right? Now, notice everything here is in, basically prime factored form. I mean, these are all powers of primes, right? So 32 seems like an oddball in that it is not in that format. So if I just go ahead and do that, remember 32 can quickly be written as, we start with 2, we divide, we get 16, divide by 2 again, we get 8, divide by 2 again, we get 4, divide by 2 again, we get 2, and one last 2 gives us 1. So notice 32 is 2 to the 5, right? So instead of 32, I'm going to write 2 to the 5 n equals 2 to the 6 times 3 to the 5 times 5 cubed times 7 squared times 11 to the 4, right? Now, if I'm trying to understand something about n, I'm going to want to add n by itself, right? So that's why we're going to go ahead and divide both sides by 2 to the 5th so that we can end up with n by itself, right? So on the left side, of course, the 2 to the 5th will cancel out. And notice on the right side, the 2 to the 5th and 2 to the 6th cross cancel, and they just leave you a 2, right? Because remember, you have 6 factors of 2 on the top, 5 factors on the bottom, and 5 of them will cancel out, leaving you 1 on the top. Or you can just use the quotient rule, right? So it's going to be 2 to the power of 6 minus 5, which is 2 to the power of 1, which is 2. Okay? So notice that now I get n equals 2 times 3 to the 5 times 5 cubed times 7 squared times 11 to the 4. Now, if I'm going to show that this expression here is a factor of n, I need to be able to write that n can be written as that number. So let me write that 2 times 3 times 5 times 7 times 11 cubed times some other natural number, right? So I notice here, I ask myself, well, 2 is here, so I don't need a 2. So what do I have to multiply 3 by to get 3 to the 5? And I see that that would be 3 to the 4, right? And what do I need to multiply 5 by to get 5 cubed? So that's 5 squared. And what do I need to multiply 7 by to get 7 squared? That would be just 7. And what do we need to multiply 11 cubed by to get 11 to the 4? And notice that's just 11. So I just showed that the number n can be written as the number that I'm trying to show that it's a factor of. So we can think of it as factor 1 times some other number. So we can think of that as factor 2. So because I was able to do that, obviously this expression is a factor of the number n. So once you understand what factors are, then all this makes more and more sense. All right, so that's a nice problem. All right, here's a clever little problem. Find the greatest 4-digit whole number that has exactly 3 positive factors. So if you think about it, the numbers that have exactly 3 factors have to have a very special form. Think for a minute what that form would have to be. How about the square of a prime? Think of 25 squared, right? That's the square of a prime, right? So what are the factors of, so 25 we know is 5 squared, and what are the prime factors? Not factors, the positive factors, not just prime. 1, 5, and 25 itself, right? Think of any other the square of a prime that you can think of. Like what about 49? We know that's 7 squared. What are the only positive factors it has? 1, 7, and itself, right? So all we have to do now is get as close to 10,000 as possible. Remember, 10,000 is when we get into 5 digits, right? So now take 99, for example, and square it, and you'll see that's going to be less than 10,000, obviously, right? So, but why is that no good for us? Well, that's no good for us because 99 itself has other factors, so it's not a prime. So what we need to do is we need to find the largest number less than 100, which is prime. Now, if you recall the numbers that we've dealt with throughout this lesson, you will remember that 97 was a prime. Now 98 is not, and 99 is not, because 98 is divisible by 2, 99 is divisible by 3. So 97 seems to be our best candidate. So because notice, if you take 97 and square it, you get 9409. So that's why this is the largest 4-digit whole number that has exactly 3 factors. Remember, 9409 is exactly 97 squared, so its only factors are going to be 1, 97, and 97 squared, which is 9409 itself. All right, very nice problem. Make sure you understand it, please. All right, this next problem, I admit the existence of it in this section is a little bit unfair. It would be better in the section where we cover the least common multiple, but it's not something that you can handle, and here I am helping you with it, so I'm making up for it. All right, so basically a child has fewer than 120 baseball cards. If he puts them in piles of 3, 5, 6, 12, or 15, he has 1 card left over each time. How many baseball cards does he have? Basically, all we have to do is find out what number there is that they all go into, right? Now, just from experience, you may be able to tell. Now, next time, I'm going to show you a definitive way of finding that, right? But for the time being, one easy way is just to look at the multiples of each of these numbers and see what is the smallest number that matches as a multiple for all of them. If you do that, like basically you just put 3, 5, 6, 12, 15, right? Just start looking at multiples of each, right? Like 15 times 2 is 30, 15 times 3 is 45, 15 times 4 is 60, and then 75, etc. Do the same for 12, right? So 12 you have times 2 is 24, times 3 is 36, times 4 is 48, times 5 is 60, 6 times 2 is 12, etc. So if you do that, you're eventually going to realize the following, that there is a magic number 60 that is a common multiple to all of them, and it's the smallest such number that is a multiple of all of them. Such a number is called the least common multiple. Now, because the division by any of these leaves a remainder of 1, right? Because they always have 1 card left over. So all we have to do is add 1 to that 60. So watch. Because I know, for example, 15 goes into 60, I know that if I just add a 1 to 60, that's going to leave me a remainder of what? 1. Check it for any of the other ones, like let's say with 6, right? Now, I know that 6 goes into 60, so by adding 1, I've guaranteed that I'm going to have a remainder of 1. All right, so it's really more of an LCM problem. It's just kind of setting you up and getting you ready for the kind of thinking you need to do in the next class. So, all right, nice problem. That's it. Make sure you can do this on your own and you understand it. Make sure to carry these on forward to see what I'm talking about, that you're going to hit 60 in each of these multiple rows, and that it's the smallest such number that will be a common multiple for all of them. All right, let's look at one more problem before we call it the day. So here we want to show how each of these numbers is composite. Now, part A, that's almost trivial, right? Obviously, this whatever number that is, if you multiply it out, is composite because it obviously has all these factors other than 1 and itself. I mean, if you multiply it out, you'll see you get this. So 3 times 5 times 7 times 11 times 13. So basically we're looking at the number 15,015, right? And we're asking, why is that composite? Well, obviously it's composite because it has all these other factors other than 1 and itself, which is 15,015. So that's pretty simple. How about this next one, right? Can we know for sure that this is a composite number and not a prime number? Now, don't think that it has to do just something with the addition of that 2, because I can take a number like, let's say this whole thing were 9. If I add 2, that's 11, so that could become prime, right? So it has nothing to do with that. So, but basically, if you notice, the first expression within the parentheses has a 4 in it, right? So if I take a 2 and factor it out, I end up with something that looks like this, right? 2 times 3 times, instead of 4, I'm going to put 2 now, because remember, I'm factoring a 2 out of this expression, right? And then times 5 times 6 times 7 times 8, and then plus 2. So now watch, with the reverse of the distributive property, I can say this is 2 times 3 times 2 times 5 times 6 times 7 times 8 plus 1, right? Notice I'm factoring out a 2 from this expression and this expression. So 2 times that gives you the first term, and 2 times 1 gives you the second term. This is just using the distributive property in reverse, right? So notice that this number has a factor of 2, has that factor, and of course itself, right? So the entire product. So therefore the number is what? Composite. So with this, I just want to give you a hint. I've shown you enough in the first two for you to be able to do this now. Do a similar kind of trick here. Of course, not with 2, but with what? With 5. And for this one, you're also going to do the same kind of trick by realizing that 10 factorial means 10 times 9 times 8 times 7 times 6 all the way to 1. And that's the hint that I will give you on that one. All right, so with that, take care of yourself, and we'll see you at the next lecture.